Alrighty. So, today we're talking. So first of all, a couple of items. About half of us are up to speed on the sapling homework thing, and that is extremely heartening to me. However, about half of us are not, and that is troubling to me. So, if you're having trouble logging into sapling, or if you need actually I don't know exactly how to do this yet. I've wasted a lot of time trying to figure it out, but if you don't know how to get more tries on the homework, like you were just messing around and used up all your tries or something, let me know and I will try to figure that out for you. um, but if you need more tries or whatever, just please let me know. Or if you need to get sapling, please let me know. Or because there's a homework portion that's in sapling that's uh, important to pass the course, and it's also important to sort of keep up with what we're doing. So anyhow, uh, uh, has anybody who's present today had trouble with sapling that they'd like to talk to me about a little bit, maybe? Or alrighty. Well, we'll that's probably better advice. We could talk about that later. But uh, so I'm just going to go forward with the book here. I think it makes sense. We're going to do a review of chemical measurements today, and I'll try to balance things a little bit for y'all because it's not all equally important. Um, Starting out with chemical measurements here, talk a little bit about SI units, concentrations, preparing solutions, and stoichiometry calculations for gravimetric analysis, although there's a good video on this from Dr. Freeman, who's doing the lab. And I will post that today. But here's an interesting foil that gives us some idea of what a measurement problem in analytical science might be. And this is kind of cutting edge stuff, but hey, whatever. So this uh, part A of the figure up here on the upper left, which shows a 200 micron, or shows an SEM image of a pulled fiber that has on the tip of it has a tiny piece of metal, probably platinum, or it could be carbon. Actually, it's probably carbon, right? But there's some sort of glass sheath, and then there's carbon thread inside, and the carbon thread is exposed at the end. And there's a method for pulling these fibers like this. Basically, you pulse you get this optical fiber into a machine, and you pulse a laser and you yank the tips apart right at the same moment, and it makes these beautiful asperities, these beautiful sharp tips. And this group here, Wang, Tong, Tong, Wang, and Cheng, have they've actually worked on this. This was started. The microelectrode business was started by a guy named Mark Whiteman at UNC Chapel Hill, and these guys seem to have perfected the technique of making these nanoscopic electrodes here, and they can measure on the picoamp scale. So pico is 10 to the minus 12 amps. And the 10 millisecond is 10 to the minus 3 seconds. So they can measure these small current spikes coming out of cells. And they used to do it extracellularly. This could also be pierced into the cell. I'm not exactly sure. But what they're looking for is exocytotic events, mainly of dopamine. So this could be some sort of a cell from the brain or the kidneys or something of some critter, and they have some extracellular stimulus, and then when that happens, the cell begins to excrete dopamine, but it excretes it in these individual packets here. So from an analytical chemistry perspective, this was a big challenge for a long time to make low current measurements on also a low time scale. So there's relatively few actual electrons are being collected on this time scale. So there's a big challenge in this type of measurement. So that being said, let's look at the SI units that people are dealing with. Now kind of a lot is made of this in the book, and I don't intend for this to go on with this at all, Meter, kilograms, seconds, kelvins, moles, amperes. These are all things we may work with. Newtons is force, and pascals is force per unit area, and then joule is Newton meter. So and a Newton, I think, is a kilogram meter. Yeah. So anyway, I forget. Sorry. So anyway, here, and then here's some fundamental units. Blah blah. We're not going to use E or C or H or any of these guys. We'll use Avogadro's number, but who cares? We might use Boltzmann constant here or there. We're definitely not using this stupid transition of cesium. It's used for calculating the speed of light, I think, and so, okay, big deal. It's, these are cool kind of physical things, but we're not going to worry about them so much. Time, length, these are the basic definitions. Don't worry about them. These are not on the exam. I tell you, these are not on the exam. Although there's a cool veritasium on this mass measurement, but don't worry about it. I mean, I basically barely understood it. So, anyway, an ampere, ampere and Kelvin. Here they say Kelvin is defined using Boltzmann constant. I'm not so sure that's true, because I have this author, Peter Atkins, and he was simply saying that temperature is what a thermometer measures. Anyway, I trust Harris a lot, though. He's a brainiac. The guy who wrote this book, he's amazing. So anyway, so moles, Kendall, da da da. Anyway, don't worry about any of these things. Radians, generated moles. Don't worry about it. So here's more nonsense here. It's just if you need to convert between pascals and all this other stuff, you can come back here. But don't worry about these definitions. It's kind of cool to go all the way back to the MKS. Like a volt is a watt per amp. It's also a joule per coulomb. And if you go all the way back to meters and stuff, it's meters squared kilogram per second cube ampere or whatever, So anyway, it doesn't matter. Now, prefixes. Here is something very apropos of today. 10 to the minus 9 to 10 to the plus 9. We actually know a bunch of things. Kilo, mega, giga, right? Yeah. I wonder who's writing on my screen. Interesting. And then there's milli, micro, and nano. on the other side of that. And 10 to the 0 is just nothing. So anyway, now this is 1, And there they all are. Yay. They have deci and centi there, which Harris sometimes uses, and deca and hecto, just to sort of mess with your mind a little bit, but we'll cross those bridges when we come to them. Okay, so conversion of units. Let's see here. I want to pick on people a little bit because I don't get to pick on y'all. Almost never get to pick on y'all. Let's see here. Okay, that's not what I want to see. Let's see here. I used to have this sort of display of everybody. It's sort of like in pictures. But I am screen sharing participants. Blah, blah, blah. Oh man, I don't know how to use this thing. Oh man. Okay, anyway. Oh well, looks like I'm not doing that. So, but so here's something from popular literature is about the ozone depletion problem. And it's interesting because recently I think the so-called ozone holes have basically gone away. And that's cool, the likely cause of the ozone hole is freon, because that makes a catalytic process in the upper atmosphere that destroys ozone, right? However, you got to be careful, right? Because we're talking about stratospheric ozone. Stratospheric ozone is ozone, and it's way high. It's like 20 kilometers up in the atmosphere. And up there, there's a lot of ultraviolet radiation, and ultraviolet causes the accumulation of ozone. But then ozone, in turn, absorbs ultraviolet. So there's this sort of steady state concentration of ozone that's maintained up there. And but down at ground level here, ozone is really kind of nasty. It's you can smell ozone after there's lightning, or photocopier rooms used to have it. Oh man, there's not that much ozone sources anymore. But it smells a little bit like bleach, and it can be a little bit hard on the lungs. So at ground level, it's a pollutant. At the atmosphere, it's important for protecting us from ultraviolet light that gets down to us. So, but this is just about converting numbers here. We have 10 to the 4th meters, and then we multiply this by this factor here, which is 1 kilometer divided by 10 to the 3rd meters, right? And this is called a unit conversion, right? And it is valid because 1 kilometer divided by 10 to the 3rd meter, it's equivalent to multiplying by 1, right? And so the way that we do this is that we cancel the meters, right? So there's meters, then kilometers. So the new unit here, meters cancel, the new unit is kilometers. And then here's pascals to millipascals, right? A millipascal is 10 to the minus 3 pascals. And so this is 19 millipascals, right? So 0.019. Another way to see this is that when you jump a unit to, like, from kilo, or kilo to mega to giga, or from, so this is no unit to kilo. This is not no unit, but no prefix to kilo. This is no prefix to milli. That you move the decimal point down here, you move it 1, 2, 3 times. So you know that 0.019, you can look at that and say, oh, that's 19 milli whatevers, right? So this is Pascal, so it's millipascals, right? So, and then here's 10 to the 4th, you subtract 4 minus 3, and you get 1, right? So that's 1.7 times 10 to the 1, which is 1.7 times 10, which is 17 kilometers. So anyway, this is how you do these conversions. And you can just work them through here. It doesn't really matter exactly how the actual number comes out. Like this might show on your calculator as 1.7 times 10 to the 1. I won't penalize you for that, although it's not totally correct. 17 kilometers is much easier to read than 1.7 times 10 to the 1. The idea of using these prefixes is to make numbers simpler, make kind of give us a better sort of psychological relationship with the numbers, So in any case, there's this, and then here's how you do it, blah, blah, blah. And you just cancel the pascals. Okay, so this is an interesting thing. In 1999, most of you were quite young at that point in time. And I remember it pretty well. And this $125 million, this Mars satellite, it just crashed on Mars. Like, oh, shoot, what happened? It turns out the stupid English were using pounds, and the JPL guys were using newtons. And it's like, and somebody gave somebody a unitless number, and it's like, and then the person assumed it was their units. I'm like, ugh. So it makes a difference here. It is rocket science. Okay, shut up, Roger. Here's a few other little things. There's imperial units, which are, based on some king's body or something weird like that, like miles and pounds and calories, whatever. And these are all basically defined by the newer unit, which is the SI unit, Système International unit. So 4.184 joules, 1.609 kilometers, 0.453 kilograms, are the ways that we define the calorie, the mile. So no worries here. We'll use these conversions when they come up. There's more conversions. And express the rate of energy used by a person walking 2 miles per hour. I don't know where they get 46 plus 45. I have no idea. But that's 91 calories per hour for 100 grams of body mass, right? They want you to re-express that in terms of kilojoules per hour per kilogram of body mass. Okay, so what I'm going to try to do here is, okay, screen sharing, yes, let me share. Here's my camera. Okay, so cool. So what I can do here is I can I can write and you can see it. Amazing. Amazing. Okay. So we want to go from calories per hour per 100 pounds. We want to convert that into kilojoules per hour per kilogram, right? So this is like, it's some sort of metabolic question, like how do you get just converting these units over from calories per hour per 100 pounds to kilojoules per hour per kilogram, right? This is some sort of walking calculation, right? So there's a couple tricks here, right? First of all, they said calories, right? And by calories, what they mean is actually kilocalories, right? A dietary calorie is 1,000 calories. So they're saying, so 91 kcals per hour. What we want to do is convert that to joules. And so we say times 4.184 kilojoules per kilocalorie, right? So the K's here, it's 4.184 joules per calorie. The K's, they basically cancel here. So I can say kilojoules per kilocalorie, right? And that's that will equal whatever that equals. Keep calculating here. 91 enter 4.184 times. This is going to be 380 uh, kilojoules per kilocalorie, right? And then we can substitute that back into the numerator here. And then we want to say convert 100 pounds into kilograms, right? 100 pounds times, what was it here? 0.453 pounds, kilograms per pound. Oops, sorry. Kilograms per pound, right? And so that's going to be 45.3 kilograms. Right? So we'll take these two results. This is the numerator here. This is the denominator here. Well, we'll just divide them out. So we got 380. Oops. 380 kilojoules. Oops, this should be hour up here. Per hour. Times 1 over 45.3 kilograms. And this is comes to 8.4 kilojoules per hour per kilogram. And it's kind of a weird way to express that unit, right? It's a power, it's a rate of caloric consumption. It's like a power. Joule per hour is that's an expression of power, and then that's per kilogram of body weight. So that's how that is done there. So let's see here. Let's see here. Okay, so let's see here. Go to a new share here. Oops, wait, no, not new share, basic. I don't know what one to go to. Let's see here. Yeah, yeah, yeah. Ah, yes, but no. Maybe. Ah, yeah, there we go. I think this is what we're gonna do. Yeah. So you guys can do this one. It's pretty basic stuff. So,
Can you once go to the question that we just did?
sorry.
Can you once go to the page where the problem that we just did, the question? Only the question.
Oh, you want me to scroll back up there?
Yeah.
Excellent. Yeah. Yeah. There we go. This is much better. And these are actually on the web. So um, that for everyone was Alvin. Thank you, Alvin. I don't feel completely like an
Yes, sir.
insane person talking to himself uh,
I
all
got it.
morning here. Thank you.
Thank you, sir.
uh, okay, cool. All right. He speaks to me as though I have a plan here. I sort of do, but not that much. Okay. so, so here we go. So, these are basic unit conversions, and the sapling homework has a bunch of questions for you to exercise your muscles in this area, and I look forward to that. So let's go do concentration. There's basically three things we have to learn here: percent, molar, and molal. Kind of going through those three things, and we're just going to beat the crap out of it here in this chapter. But it will help you immensely as we go forward. So some of it will be review, and some of it will be new, but we're just going to go on through it. So first of all, some review. Solution is a homogeneous mixture of two or more substances. So, basically salt dissolves in water, sugar dissolves in water, whatever. It's homogeneous because, even with a microscope, you can't see the individual bits floating around, and, that distinction, breaks down at the molecular level, of course, but when we're talking about analytical chemistry you might do in a lab, any solution that's if you take a microliter or whatever and you can't tell the bits apart, then it's definitely homogeneous, right? Then the solute is the species that's dissolved, and the solvent is the a major species. It's the thing that dissolves the solute, right? So um, uh, we're talking in this course about aqueous solutions 99% of the time. In other settings, you'll use a non-aqueous solvent. And, you just have to bear in mind that, solute and solvent have this relationship. Solvent is the major species and solute is the minor species. Okay. So moles, atomic mass, molecular mass, blah, blah, blah. I'm not going to go over them. Concentration, quantity per unit volume, and there's basically there should be a third here, right? But molarity is moles of substance per liter of solution. Molality is a weird one here, and I personally have not seen much molality in my practice as a chemist. But for some reason, Harris has chosen to emphasize this, and he's a pretty smart guy, and so I'm like, okay, all right, let's do molal too. It's super easy to prepare a molal solution. You just need a balance, right? It's moles of solute per kilogram of the solvent, right? So if you can weigh the solvent and weigh the solute, then you're good. You never need to measure volume to get molality. And molality is also temperature independent. So if the solution expands or contracts thermally, then the molality stays the same. Whereas the molarity, you kind of have to define at a given temperature. So there we go. So let's see here, and we'll get to percentages next, but that's the third concentration unit we want to get. Molarity and molality, and then formality. There's a formality is creates some confusion, and it really only comes up because when you talk about substance that dissociate or undergo some change in solution, not necessarily a full-blown, formation of a new chemical bond, but could be dissociation into ions. That you have to sometimes you need to just talk about the amount of stuff you put in as being the formal concentration, because you may not know how much acetate ion, how much protons you have left. Could have been base in there that's sucking this over to the right, or acid that was pushed to the left, or something like that. That it could be a common ion effect that is messing with the amounts of acetic acid, but you want to just talk about the amount that you originally put in of this solute here, acetic acid or whatever, when you talk about its formal concentration. And that's just the molarity, but irrespective of dissociation or other kind of reversible chemical reactions that can take place after that. So right, so here's an example, right? So magnesium chloride. Magnesium chloride, when you put it into water, you can assume it fully dissociates into magnesium plus 2 and chloride minus, but that's not quite true, because about 70% goes in, right, at 0.05 molar. It's a concentration dependent thing, right? But at 0.05 molar, 70% is magnesium 2, and 30% is MgCl plus, right? It's the magnesium and the chloride ion remain associated. They remain bonded in solution to make this monopositive ion, right? So, how, and about 0 is the undissociated ion pair, right? But if you make this 0.05 molar, it's actually 0.05 times 0.7 in Mg plus 2, right? But it's still 0.054 mole, right? So it's, anyway, irrespective of dissociation. Right? So, okay, so let's just do this calculation here. Let's see. How did I do this again? Advanced. Yay, there we go. Okay. So, so what they're asking us here is to calculate the molarity of sea salt here. So okay, hold on, I'm gonna. Okay, so I'm gonna copy down the problem here. So this is 2.7 grams of NaCl in 100 milliliters of solution. Seawater solution. This is part A. And part B is 0.054 molar MgCl2. And then we want to say how many grams of MgCl2 are in 25 milliliters of water. So let me get back here. Come on. Make sure. Contact from second camera. Share, please. You guys can't see the document camera, can you?
Nope, only the white page that we have.
Okay. Oh, can you see what I wrote down, like with the pen and
Yes.
everything? Oh,
Yes.
okay. Oh, weird. I can't see it now. That's so strange. Okay, well, I'll just write. I don't care. I have to see it on the screen. So, and this top one, this one goes to what molarity? So, 2.7 grams of NaCl, right? And then what we want to do is we want to multiply this by the formula weight, right? So we can say 1 mole over 58.44 grams. This is moles of NaCl. Right? And then what we want to do from here is we want to divide by the liters of solution, right? So this is take the number of grams of sodium chloride, convert that to moles. It's a unit conversion. Just take 1 over 100 mLs. We want to cancel the mLs, right? So we need 1,000 mLs per 1 liter, right? And this all comes out to 0.46 molar. Right, this is part A. I can't see what I'm writing here, so you guys have to let me know if it's coming out weird. And then part B. Oh, thank you. Okay. Part B is we've got MgCl2, which is 95.2 grams per mole. And so we're going to take 0.054 moles of MgCl2 per liter of solution. then multiply that by, again, 1,000 mil, and then 1 liter per 1,000 milliliters, right? And then we're going to multiply that by 25 milliliters, right? Now the liters are going to cancel, the milliliters are going to cancel, and now we're going to have the unit left over will be moles of MgCl2. Now we just have to convert that to grams. So we're going to say 95.2 grams per mole. And this comes out to 0.13 grams.
Yeah.
Excellent. Alrighty. So let's see. I think there's more exercises up here. So let's try this guy here.
Professor?
Yes.
On the top portion where you wrote MgCl2 equals 95.2 grams, what did you write underneath the 95.2?
Oh, this is Sanskrit for mole. Okay, that was a joke. This is 95.2 grams per mole.
Gotcha. Thank you.
No problema. Let's see here. I think I messed this up, so hold on. Okay, so let's see here. I'm screen sharing. Aha, now I can see you guys again. You know, it's PowerPoint messes this thing up. PowerPoint's problem. Okay, so if I do this, now I do this. I say share. No. You guys can probably see the document camera now. Ah, there it is. There's my document camera. Sort of fuzzy, right? It's got this stupid autofocus thing that's like focusing. Okay, so I'm going to keep going. Okay, let's do percents. Let's do percents. Here we go. I'm just going to use it like a full screen thing, like here. I don't care. Whatever. You guys will get over it. So, percent composition is important to get here too. So there's basically two types of. Oh, so can you guys see the PowerPoint thing here?
Nope, we can still see the white page that you have written.
Okay, got it. Thank you. Okay, new share, basic, screen 2. Okay, now you see the percent composition, right?
Yes.
Oh, cool. Okay. So, anyhow, so oh, this is so strange. I think I know how to defeat this. So you just see my second monitor. I think I know how to defeat this. Hold on just 1 second, then we'll do percents. Let's see. Your screen sharing. Okay, got it. New share. Advanced. Portion, content. Basic. Just do screen 2, right? So if I do screen 2 here, right, you see my friend Walter, and you see this PowerPoint thingy up here, right?
Yes.
Yep.
Yes.
And then if I were to be so bold as to put the stupid webcam up there, I know how to do this. Hold on. Camera app. Computer's starting to overheat now. And now you see that's my face. Okay, hold on, wait. No, you don't want to see that. Let's see here. Let's see here. Where is my camera? Camera. Framing rate. Okay, so that's not right. Okay, I know. There's a sort of a application that comes with this webcam, which is Aha, there we go. Okay, so now I've got this guy here. So now I can sort of switch back between them, right? So now you can see the whole mess, right? Okay, cool.
Yes.
Yay, good. I'm sorry, you guys. This software is too slick for me. Okay, so real quick now, percent, right, is either mass of solid per mass of solution or volume of solid per volume of solution, right? And there's a couple ways that comes up, right? And the most important way is weight percent to molarity, right? Weight percent to molarity, right? Molality is like, not so important, right? So, right, but molarity is real important. So, in this actual problem here of taking percent HCl or whatever and then converting it into molarity is important. So let's do this guy. Okay, hold on. I gotta get the things copied over here. So let's do the 37% weight of HCl, and density is 1.19 grams per ml. So let's calculate the molarity. Molarity is capital M. That's moles per liter. Right? So we're going to say, I'm going to start with this definition. This is 37 grams of HCl of this molecule per 100 grams of solution. That's the percent weight yield. So now what we're going to do is we want to move towards moles per liter, right? So, oops, make this bigger now. Oops, I know what happened. Oh no, wait. Not doing that. Okay, we're going to move towards moles per liter, right? So, 37 grams. So, so this, we're going to need the density to turn that into liters. And this, we're going to need the formula weight of HCl to turn that into moles. Right? So 37 grams, and we'll put 100 grams of solution down here. And we'll multiply that by 1 mole. Excuse me. 1 mole of HCl. Let me peek. It's 37. Right? 30. Anyway, it's 36.5 grams of HCl. He states confidently. And then, so this is going to give us moles per 100 grams. So this grams of HCl is going to cancel. Now to go from grams of solution to liters of solution, use the density, right? We need the milliliters to be down here, right? So we'll say 1.19 grams of HCl solution for every 1 ml of solution. So grams of HCl solution here is going to cancel there. And then we're going to calculate the, we'll just convert that to 1,000 mLs per 1 liter here, right? And then this comes out to, let's see if I can do my calculation. 37, enter, 100 divide, 36.5 divide,
12.1.
1.19 times, and then 1,000. So I get 12.06
Yes.
molar. Right? Does that sound right? Excellent day.
Yeah.
Okay. So what we can do for Thursday is we can work on there's 36 sapling problems, and it's called chapter 1A, right? So work on these. Eventually, we want to do all of them. And then I'll have to assign a due date, but I want everybody to have access to stuff before I assign a due date. So right now, this is sort of the assignment right now, is to do these sapling problems. All righty, guys. Any complaints, questions, anything like that?
Professor, are we gonna have these slides updated on the Canvas?
Oh, yes. They should already be there. They should already be under files, in Canvas under files. If they're not, then I am completely bogus and I shouldn't be a teacher and I should be fired immediately. But they should be there. So take a look and I'll take a look. But the check in Canvas under files. Does that sound good? Okie
It
dokie,
looks
guys.
like in the chat they're saying that the files aren't there.
Wait. Hold on. I'm going to figure this out. Okay, let's see. 55, blah, blah, blah.
Oh, now someone
Files.
is saying the old one isn't.
Hold on. Files. Oh, there's chapter 0. So I just got to put chapter 1 up here. Does this make sense? It's under 55 files, chapter 0.
Yep.
Okay, cool. So they'll be here. I'll put chapter 1 up there. All right.
Thank you.
Alrighty.
Thank you so much, guys. Thank you so much, guys. Thanks for hanging in. It's a weird experience, but we'll get through.
Thank you. Bye.
Bye.
Thank you, Professor. Have a good one.
Thank you.
I have a question.
Yeah, what's your question?
Is it okay if you post the slides before class? Because I want to go through
Oh,
them
absolutely,
and look at them on my phone.
absolutely, Cindy.
Yeah.
Absolutely. Yes.
Thank you.
I will definitely do that. Thank you so much for
Thank
that
you.
suggestion. Okie dokie. Cool. Okay, bye-bye.
Absolutely, Janice.
Hi, baby.
Hi. Hello.
Hello, Mitra. How are you?
Good. How about you?
I'm good, babe. How are you, sweetie? Did you enjoy the lecture?
Yeah, it's a bit slow, Steve.
Yeah.
And Roger, that unit, mole per kilogram, we use that in industry a lot because we don't have density all the time.
There you go. This is why I need you, baby. This is why I need you.
So, and if something is not important, baby, just move on.
This is why I told you not to come on, because you're gonna have all these critiques, and I'm not ready for you.
But
That's okay.
otherwise,
That's true. It's true. It's absolutely true. Thank you, baby. Okay.
Mom
All right.
Mariam. Yes, Mom Mariam.
Okay. Hello, Mom Mariam. Okay.
Okay,
Bye.
honey. I have an appointment at 10. Talk to you later, babe. Bye, hon.